So hello everyone. In last class we have seen this introduction to Hopfield recurrent network. This is a single layer feedback. This is a special case where input is coming from this nodes along with this initial conditions that will go through these neurons, and output computed is coming back. Okay, so like this. So all the outputs are coming back from front side, and important thing is self feedback is missing, and second most important thing is weights are symmetric. What it means, when I take this connection, say from first node V1 to suppose the second neuron, it is the W21. So W21 is equal to W12. Where is W12? So from first neuron to second input. So this connection has weight W12. So this connection from second input to first neuron and connection from first input to second neuron, they are same. Okay. So like that, W31 equal to W13 and W34 may be equal to W43 and so on. So every connection here, when I flip the numbers, it's same. So that means the matrix is symmetric. Since self-feedback is absent, so W matrix has all the diagonals 0 and all the entries on the top are equal to all the entries in the bottom. So that's why it is symmetric matrix. Now the net that is coming to these neurons is given by this equation, as we have seen in last class. Now let us discuss the energy function of this network. So that is the heart of this discussion. You will see that the energy function of this network is defined by Hopfield like this. Okay, so this is inspired from some physics formula and physics phenomena of say tiny magnets, but let us assume that this is our energy of the network for time being. We will not enter into details how this equation has appeared. Okay, those who are interested, they can read further in Hopfield paper, or there are many uh, literature available. You can go through that. So for time being, let us see that, say this is the scalar valued energy function for the system that we have seen, which is in quadratic form. Now the scalar valued energy function of discussed system you can see here, and I can compute gradient of this energy. So gradient of this energy is equal to, if I take this equation, okay, and try to find out gradient of it. So you can see a small step here. So gradient of x transpose y with respect to x is equal to y. When I take gradient of x transpose ay, so ay, A is a matrix, x and y, these are two vectors. So when I take gradient with respect to x here, I get ay. Okay. Then when I take gradient of x transpose Ax, in this equation it was x transpose Ay, now here it is x transpose Ax. So if I take gradient with respect to x, then it is Ax plus A transpose x. Okay, you can check this thing in algebra book. Now when I take gradient of this energy with respect to V, so this is similar to this thing. Okay, so you can easily find out this by using this, and this is also using equation say A. You can solve easily equation B, you can solve. So when I take gradient of this equation with respect to V, then for the first term I get this quantity, and for the second I get this, for third I get this. Now when I put in this equation W transpose equal to W, so what it means, I assume that weight matrix is symmetric. Okay, weight matrix is symmetric. So that's why if I put this thing in equation say C, then I get the gradient of energy with respect to V like this. So this W transpose is equal to W, so this will be twice W, and this half will get cancelled out. Okay, so this equation is now minus WV in minus I transpose plus T transpose. Now this is gradient of energy. Okay, now the energy increment you can calculate by multiplying this gradient by change in V. So change in V, that is input, change in input multiplied by gradient of energy, that will give you change in energy. Okay, so let me write here, change in energy is equal to gradient of energy multiplied by change in V, that is input. Now what we do, since only one output is allowed to update at a time, so if, I think I have discussed in last class that we will allow only one neuron to update its weight, update its output. So in that case, change in V, say this vector, this is a vector, there are many neurons here, so this you can write this as delta V1, then delta V2, and so on, up to how many neurons you have. So only if I change ith output, then only ith neuron is allowed to change its output. So that our earlier equation of change in energy you can simplify. Here if you see closely, these are all big things. So this is a matrix, this is a vector, this is another vector, this is another vector, and this quantity here is multiplied by another vector. Okay, so this is a big thing. So when I put the condition that only ith node is allowed to change, then that equation has changed to this thing. So if you see this gradient multiplied by this change in V has turned to this equation, where only ith related terms do exist and others are having same value, so they are not changing their value, you can throw them. So only one neuron is updated, so this is the case. So this can be rewritten as change in energy minus, so you can take this in detail. So this product W transpose Y is nothing but summation J equal to 1 to N Wij into Vj plus initial input Ii minus the threshold Ti for ith neuron multiplied by change in input Vi. Now here J is not equal to I because Wij where I equal to J is 0. There is no self feedback. So that thing you have to keep in mind. Now when I go like this is nothing but it's a net value for ith neuron. So it is net I. So this bracket is net I multiplied by change in input. So this change in input is as it is. So net I is the input of the neuron whose output is allowed to change. Now when net I is less than 0, when net I is less than 0, then change in Vi is also less than equal to 0, and when net I is greater than 0, then change in input Vi is greater than 0. So these observations stated here mean that under the update algorithm, the product term net I into change in Vi is always non-negative. Thus, any corresponding energy change is also non-positive. Therefore, we can conclude that the neural network undergoing transition will either decrease or retain its energy. See what it means. It means that this change in energy, I can write here, change in energy is some negative quantity of net I into change in Vi. Now what these statements are saying that this bracket is always positive. What it means? The change in energy is always negative. That means it is keep on decreasing. So when you iterate with change rule, that is one node is updated at a time, if that is fixed, this rule is fixed, then you will find that your network is always losing energy. At the most it can retain whatever it has, but it cannot gain the energy. Now why I want this kind of a thing? Because I want, when I give some initial input to the network, it will eventually fall down into a minima, and minima will be the location where I have stored the pattern. Since this Hopfield network is working like a memory, I want to store some pattern, then I can use this network. Now whichever pattern I want to remember, I have to create, using the weights of the network, a minima at that location. Once that is done, then whatever may be the triggering input in the vicinity of this minima, your network will land to minima and it will recall what is stored. Okay, so that is the basic idea. Now what I am saying is this product is always positive. Do you agree with this? If this net, say net I is greater than 0, okay, this net I is greater than 0, then we have two conditions. Say Vi was suppose -1, then Vi new will be +1. So Vi new minus Vi old will be positive. Okay, and since net I is already positive, so positive multiplied by positive will give you a positive result. Okay, now suppose net I was less than 0, okay, and your output was positive, say Vi was positive, then Vi will become negative, then -1 minus of +1. Am I right? Earlier it was -1, sorry, now it is -1 and earlier it was +1. So -1 minus of +1, that will be -2 multiplied by net, which is already a negative number. So negative into negative will give you positive. So you can check for all the other two combinations, then you will find that this quantity is always positive, whatever may be the condition of net and change in V. Multiplied by negative, so the total you can say calculation is that this change in energy is always negative. Again I repeat, it means that it will lose energy, that network will lose energy as time passes. Now this diagram may give you a better idea. Now here it's a 4 neuron network. So there are 4 entries in the output. So this is output vector with different possible combinations. So since there are 4 neurons, I have 2 to the power 4, that is 16 possible states of the Hopfield neural network. Okay, there are 16 possible locations. You can see here, this is the topmost, that is 1 1 1 1, all 4 ones, and this is the bottommost or initial very uh, first position in the network. And what is done here is you have pattern stored, suppose this one, because you can see here a self loop like this. The figures in the bracket here are showing you the energy of network for this state. Now suppose what happens if I give you initial trigger like this, say that this is my initial trigger to the network, say +1 -1 -1 -1, then the initial energy of the network is +2. Now from here network will try to change its energy, it will fall. Now suppose you allow say this bit or this neuron to change its say output, then you will see that you will move from this point to this point. Okay, so this has become positive. Now you can see energy was 2, now it has gone to 0. Now if you allow the next bit to change, say this bit, then it will follow this path and land to this. Okay, so all of them are now, these first three are now plus, and energy has gone to -6. Okay, so energy was 2, then it has gone down to 0, then it has gone down to 6. Now this is the lowest possible energy in this network, and you can see when you iterate here onwards, then you land to same point. Okay, your output will not change. So output is always 1 1 1 minus 1. So initial input was 1 minus 1 minus 1 minus 1, then you land to 1 1 1 minus 1. So this was stored pattern, and this is initial guess. Okay, initial trigger you can say. So for initial trigger this, you will land to this, provided you do this sequence of changes. Okay, now this thing we call that we have stored this pattern in this network. You may find another pattern here which is also stored with values -1 -1 -1 +1. So for this again you will see that energy is -6. Now what happens when you randomly give some input? Say you start with this point, then you land to this. If you start this point, you land to this. Even if you start here, then you will follow some path and land to this. So say the area like this is the vicinity of this pattern, and area around this pattern, second pattern, is the vicinity of this. So when you land to this side, it will attract to you. This pattern will attract you. When you land to this side, this pattern will attract you. So I can say there are two stored patterns in this circuit. Okay, I hope this idea is clear. Now we will take one example how this is done. So let us say there is a circuit with weight matrix like this. For the threshold and external inputs assumed to be 0, find energy function. So this is our first question. You have to find out energy function of this network. So network is simple. I have 4 neurons. So you refer to Zurada's book for this. If there is a solved problem, you try to understand similar to this. So you have input here, say V1, then you have second input coming from this side, then there is a feedback from this side, there is another feedback from this side. So this is the circuit, and from first input you have connection with all remaining nodes. From second you have connection with all nodes except second. Then you have structure like this. Okay, now for these connections weights are like this. So this is V1, V2, V3, V4. Since initial input and thresholds are 0, so the other terms related to that are absent. Then I have the remaining thing as -12 into V transpose into W into V. So this is V transpose, this is W, and this is V. Say minus I transpose V minus that threshold some threshold transpose V. So these two things are 0 since it is given to us. Now what is left is only this. So what is asked to us is to find out energy function. So what you do, you take this vector, you multiply inside, and then whatever you obtain, you multiply with this vector. So you should get this final outcome as energy function. Okay, so somebody asks you what is energy function, then this is your energy function. The system produces discrete energy levels for values -6, 0, and 2. Now, how do I came to know? So for that, what you will do is you can try at home that I have 4 inputs. So I can write here V1, V2, V3, P4. Then I start with the minimum possible combination -1, 1, 1. Then I can keep on changing values of V's. So like that, I can, it's like a binary number. And then you will go up to +1, +1, +1, +1. Now for these combinations, you will find out from equation what is EV. Suppose I take this -1, -1, -1, -1, what is energy at this point? So you will substitute here, say -1, -1, so minus minus, it will be +1. So this -1 multiplied by -1, so that will be +1 minus, so this will be -1 into -1 minus of -1, so +1 plus -1 into -1. Okay, so you try to solve this, so it will be, I think this will get cancelled out, so this will be -1 and this will get cancelled out, so this is 0 plus 1 plus 1, -1 into -1 is 1, so minus, so total I think it is coming as 0. Okay, so energy here it will be 0. So like that you have to compute for all 16 combinations. So you will find that you will get only 3 numbers, 0, 2 and -6 throughout this table. So this table will consist of only 3 numbers, so 0, 2 and 6, that you can verify. I can then say that my system has only 3 discrete energy levels, that is -6, 0 and 2. Now next question, if V0, that is initial vector, is -1, 1, 1, find the output of network if we update nodes in sequence 1, 2, 3, 4. So what it means, some initial V is given to us, so this V is provided, and we have decided that we will update this network using the sequence first node first, then second, then third, then fourth. Okay, so then find the output of network. So what is to be done now? In this case, this W is given to us. Now I am dealing with number 1, that is node 1 or neuron 1. So I will take the associated weights like this. So this is node 1. I take this weight, I write here in transpose form, and then I multiply with V0. So this is V0. Okay, then you will see that the multiplication is +1, sine of that is +1. So activation function is sine function for this network. So you will get +1. Now initially the position number 1 was -1. Now you will see that since I am allowing first neuron to change its output, it has changed or flipped from -1 to +1. So I have to change now V0. V0 was -1 +1 +1 +1. It has changed now to V1. So the first position is now changed. Okay. So the new output vector is +1 +1 +1 minus and +1. So all +1s. Okay. Now what is to be done? So this is my output due to flipping of first position. Now I allow this second position to flip. If required, it will flip. So what I do, I take this second weight, second row from this matrix, okay, and I keep here. And then I multiply with latest copy of V, that is V1. Okay, so then you will see that this is again positive. So sign of 1 is positive, so it is 1. Okay, so second position was positive here and it has remained positive. So even if I allow to flip that position, it has not changed. Then we take the third uh, position or third bit. That means I should take this row now. So this row will be here 1 1 0 -1, and then I multiply with latest copy of V. So what was latest copy? Latest copy was all ones, right? So this bit was allowed, but it has not changed. So V1 was equal to V2 only. So I will write here the third position, the third neuron, 1 1 0 -1, and that will get multiplied with all ones. So this will be 1 plus 1 plus 0 -1. So this will be resulting into +1. So sign of +1 is +1. So again V3 is equal to V2, since this bit was allowed to update but it is not getting updated. So its update value is same. Then you take the fourth neuron, because now that neuron has got the chance to update. So you apply this same input, you multiply this. So this is -1 -1 -1 plus 0. So this will be -3. This will be equal to sine of -3. So output of neuron is -1. So now V4 has changed to +1 +1 +1 -1. This bit was allowed to update. Now it has updated itself to -1. But my sequence is over now. Sequence was 1 2 3 4. So all neurons were allowed to update, and they have changed their values if required. And this is the final vector V4, which is now which will be now used to change first position again. So we will now enter into second iteration. In first iteration, neuron 1 was allowed to change, then second, then third, then fourth. Now we will take the latest copy of V and we will go back to neuron number 1. We will allow again bit number 1 to change its value. So like that we have to iterate in this loop, and we will terminate this process when this V when I iterate through this complete chain has not changed. That means suppose I take this vector 1 1 1 minus 1. I start with this and then I go to bit number 1, neuron number 1, allow its value to change, then it has not changed this vector v, then I go to second, third, fourth, all of them have not changed their values. Then v5, if it is equal to v4, then stop. Okay, so that means you have reached the minima or the pattern which is stored in that network. Okay, so as per our problem, we started with this position. Initial vector v 0 was minus 1 1 1 1. Then we allow the first bit to change. It has gone from this position to this position where all were 1. Okay, that means this bit was changed from minus 1 to plus 1. So energy was 2, then energy has become 0, that is reduced. Then from this bit onwards, I am allowing second position to update. So it has gone to this position. After I allow the fourth bit to update. For second neuron, third neuron, there were no changes in the output. But when I allow fourth one, then it has flipped. So this position was flipped when I change or allow output number 4 to change. So it has become minus 1. So that has become minus 1 here. Now you see that energy has reached to minima in this circuit, which is minus 6. Now here onwards, if you iterate, you will get same output. Okay, that means we have learned to minima or stored pattern. Okay, so this is how this network works. In next class, we will see how to design this. We have now ready-made circuit, but we have not seen how to design this network for patterns that I want to store. That means for given patterns, how to create minima for that pattern. So that we will see in next class.